So next we have Andreas talk about mutually iso-recursive subtyping. Thank you.
Yeah, thank you very much. So I'm glad to be able to present a talk that is like purely about type system stuff and does not mention WebAssembly at all, except on the first slide. Just as motivation, why do I care? So we recently extended WebAssembly with support for garbage collection, and that required extending the type system with things like subtyping and type recursion. And doing that, of course, since this is like inside a VM, so this involves runtime type checks and everything, it was important that this is like performant, right? So these checks that we have to perform on types have to be fast. They also have to be structural for modularity reasons. I won't go into that here. But yeah, so that meant we had to do something, and to give you like a little example, here's like a stupid structure that is recursive in just some pseudocode language, so you can see that C is recursive with itself, and you would lower that to like a more type-theoretic recursive type that looks like, oops, sorry, that looks like this. What's going on here? Yeah, like this. So I'm writing a sort of record here with curly braces, but it's really just a tuple. I erase the labels just so make a bit more readable. So when you see that we have these mu types here, you probably have all seen that, and the alpha refers to the type itself from the inside. So that's how we write recursive types. But what does that mean, right? And literature has two different semantics, roughly speaking, for recursive types. The first is like the equi-recursive semantics, where a recursive type is always equivalent to its unrolling, like in every context. So this is just like a universal rule. And what that implies usually in the common interpretation is that this is like a co-inductive equivalence relation. So you get the largest fixed point of your equivalence rules with this rule. And also in practical languages that employ this, semantics usually keep the recursion between types implicit. So you just have equations essentially. So in a way, this is like a nice semantics because it's the most permissive you can find. It's the largest fixed point, right? So in a way, it's a canonical choice. Unfortunately, it has a number of downsides which have to do with the complexity of the meta theory, and in our case specifically with the algorithmic complexity, because the algorithms we care about, like equivalence and subtyping and canonicalization, they are actually equivalent to similar algorithms on deterministic finite state automaton. So these are like not at all linear algorithms. So this is not really an option for something you want to do in a runtime. Believe me, we tried. It's way too expensive. So the other option then is iso-recursive types. So we looked into this. So iso-recursion differs in that you have explicit term level introduction and elimination forms for this mu type. So you have to use them in the right places. And there's no implicit unrolling anywhere. You only unroll through these operators. And that is nice because it actually provides an inductive semantics, at least in the common interpretation of these. For types, you just have inductive terms, and that results in the smallest fixed point. But you also have to make recursion explicit usually. So this is less permissive, but just as a side remark, there's an interesting result by Abadi and Fiori from the 90s that shows that you can actually encode every derivation in a system with equi-recursive types if you're willing to pay the price of pretty expensive conversions for every use of subsumption. But yeah, the upshot is all the algorithms we care about are like mostly linear. Not truly, but in the first approximation. So this is nice. So let's go back to our example. I showed you this. Let's change it a little bit. So this is just like a single type that's recursive, but now let's consider a variation where we have two types that are mutually recursive with each other. So we would want to lower the first type like I showed before. It would result in something like this, where inside we have D, right? And if we do the same independently with D, then we get something like this there. And the problem now is that, of course, they kind of refer to each other, so there's no closed form for either of them, right? So what do? Well, the usual thing you want to do is you break the recursion by substituting one into the other. But since they're both closed, you can't do that directly. The thing you have to do is you substitute D in there, but you also have to modify it so that its occurrence of C is replaced by the recursive variable alpha C there. This way you get a closed form, and you can put that into D, and both are in closed form. Note there that, yeah, I had to modify the type. So this is actually a different type that I've inserted there, right? So it's syntactically different, and that under the iso-recursive semantics means it's actually a different type. But this looked okay so far, but let's try to scale it. So here are 3 mutually recursive types. We translate them like this, starting like this, and now we want to substitute backwards, essentially. So these are the 3 places that are forward references. So let's start with the middle one with C. We did what we did before, and now we have to go on from there and substitute B into A, and that goes like this. And then we also have to do the same thing for C, and that goes like this. And once you stare at this a bit more and think about what this does in general, you simply quickly see that this is exponential, right? And also, all the occurrences of the recursive types, they are all different, right? So it's really exponential. You can't even share the representations. So this is kind of a bummer, right? Like all the literature, like assuming, oh yeah, these iso-recursive types are nice because we have this linear algorithms. But when you actually want to encode practical type definitions, you have an exponential encoding. So that kind of breaks the whole promise of that they have. So what do we do? So one folklore solution is to go to higher kinds, specifically introduce tuples of types, so tuples at the type level, and then lift the mu operator to tuple kinds. And that, for example, is the thing that has been used in the Harper-Stone semantics, the type-theoretic account of standard ML. And if we do that here, the way you would encode this is now as a single mu over a type tuple, right, of these 3 different types, and then you project from them. So the alpha is actually the triple of all, and the first, second, and third projection are the individual types, and you can define abbreviations to get like the original ones. And that is linear in size, right? So problem solved, supposedly. That's what I thought, but we also have subtyping. And subtyping is not actually simple, this contrary to common belief. So it breaks everything. So this encoding does not actually work with subtyping. Let's see why. So let's switch to a slightly more practical example, like a tree we model as like 2 types. One is the forest of its children. So they are mutually recursive, and the forest is modeled as a linked list, essentially. So we would lower it as before, as this combined thing, and the 2 projections from that. Easy so far. But now assume we are in an object-oriented world where we have subtyping, and under object-oriented ideology, of course, I should always be able to extend any given type to a subtype, right? So I should be able to define something like this that adds a field to, say, tree, which records the size of the thing. And note that this is not actually a recursive type at all, right? So we can lower it, or should be able to lower it, encode it completely independently to something like this, which looks fine. And just for uniformity, I introduce a mu there, although it's not actually recursive, but it doesn't really harm. But, okay, that's an encoding, but we also want this to be a subtype, right? So we want this to hold. That's kind of the main thing we want to achieve here. Well, does this hold? To understand if it does or not, we have to look at the subtyping relation, how that's usually defined. So for mu types, what you usually employ is the so-called Ember rule, because it was first used in the 80s by Cadelli in his experimental Ember language. And that says that 2 mu types are in the subtype if their bodies are, assuming the variables are, right? So that's kind of like straightforward rule. The other thing we have to look at is how you subtype tuples of types, and you can do the straightforward thing here, which is like pointwise. So in this case, I actually require them to be the same arity. You could also add width subtyping if you wanted. But turns out that doesn't actually help because we can't, given these rules, we can't prove this, right? It's not possible, and there's no way you can tweak these rules to make that work. So there have been various generalizations of iso-recursion mentioned in the literature, and the ones that might be most that might be relevant here are a paper by Ligatti and others a few years back who generalized this subtyping rule for mu's to basically unroll on both sides. This is a bit more powerful. It turns out this is actually just a special case of something that was already suggested by Zhong Shao 20 years earlier, which is just to have a general unrolling rule for mu types. So you have this unrolling equivalence everywhere. But if you stare at this, or if you try to work through some example, you immediately recognize, well, this is all nice, but now we are back in actually co-inductive territory, because this rule is like no different from the equi-recursion unrolling rule, except that you keep the mu around, right? But you have all the same cost with respect to algorithms. So in a way, this is kind of useless, right? So what do we do? What these extensions have in common is that they try to enrich subtyping, right? So they try to basically infer a larger, richer relation from at the use sites by extending or generalizing the definition of subsumption and subtyping. What if we went the other way around? We look at the declaration side where we form these terms and require to declare something there. So we move from the use side to the definition side of subtypes, vaguely speaking, intuitively. What do I mean by that? Really, it turns out that you can boil this down to a very simple idea, which is we put upper bounds on mu types. So instead of having this, I propose we have this. And this is kind of a very natural thing to do if you're in a system with quantifiers and subtyping, right? So we have all these other bounded quantifiers, so we just say mu looks like the same thing. But that is just syntax. What does it mean? What does it mean? So, okay, let's first assume we have the usual subtyping rules like reflexivity and transitivity. So what's our rule for mu now? And it becomes a very simple rule. We just read it off. So the only direct supertype of mu other than the reflexive case is what we actually have written as a bound. And there's no premise here. We just vacuously assume this to hold because that's what we declared. So that is a bit strange. Obviously, that can't be all, right? So we have to check something. But the thing we check now, that moves to the formation rule now. So it's only okay to form such a type in the first place if there's something that holds. So of course, both the types in there have to be well formed, but also they have to be in a suitable subtyping relation. So the body T2 has to be a subtype of the unrolling of its bound. What's the unrolling? Simple thing. So there are two cases. Either the bound could be top, and then it's just unrolling to itself, or it's actually another mu type, and then it's the usual thing for unrolling a recursive type. So this way we check that kind of the bound, the type and its bound are actually in a suitable relation. So let's look at an example if we use this. So we could now encode this as follows, and this is almost the same as before, except that we now have this bound there with a pair of two top types. So this case is not particularly interesting. We only have top as a super type, but where it gets interesting is here, because this now has a non-trivial bound, which is tree, right? Because that's what we want to achieve. So does that work? Well, first of all, we wanted to have the subtyping relation to hold, and well, that is kind of trivial now. We can just read it off, right? We declared that it's holding. But of course, we also have to check that this is actually a well-formed type. So there are two things we have to check there. The first is that, well, the body is well-formed, and that is kind of straightforward here because it's not even recursive. So assuming forest is already well-formed, that is trivial. And the more interesting thing is we have to prove this. And if we perform like apply the unrolling function, it gives us this. So that is the body of the tree forest type with all the alphas substituted by tree forest itself. And using these abbreviations we have, we can kind of simplify to that. And then we can apply some type level beta equivalence for the projection there, which gives us this, and that is just plain recursive subtyping. So this works. Yeah, this is actually just, that's the basic idea. That's all I wanted to show. In the paper, of course, I go quite a bit more general, so I generalize this to a full higher order subtyping calculus, so you can have lambdas as bounds, which allows you to encode subtyping between generic types. So it's actually doing the full F omega subcalculus, basically being a minimal extension to that calculus. And I do all the soundness and decidability proofs for that based on the work by Pearson, Steffen, and Compagnoni from the 90s. Long proofs, but yeah, it all works out fine. There's also somewhat of an extension in there that you need a little bit of extra thing when you want to have recursion or subtyping within a recursion, like between different types that are defined in a recursion. You do need to do a bit more, unless you actually add f-bounded quantification. So this system does not have f-bounded quantification. I just left it out because it's mostly orthogonal. Another thing I do in the paper, I show that you can actually encode the subtyping of relation of featherweight Java into this. Featherweight Java minus f-bounded quantification, because we left that out, and prove that this is correct embedding. And then I define a fragment of this calculus, because like the full higher order calculus is still pretty expensive. When you've checked subtyping, you have to do all sorts of substitutions, deep substitutions deeply into terms, right, into type terms. And that's not something you want to do in an engine, for example. So you want something similar. So I define a syntactic fragment of the type language, which ensures that all substitutions that you have to perform for subtype checks are actually shallow. So you never have to go inside a mu, actually. And when you stare at that, what you realize is we have basically reconstructed what nominal subclassing does, except that we still have a structural type language here. So when you have two mu types that are structurally the same, they're still equivalent, despite, but at the same time, if you were to canonicalize all the types in your program, like make all the equivalent types the same, after that you can treat it as if it was just nominal subtyping. So it's behaving like nominal subtyping up to this canonicalization step you do before. And the upshot of that is that you can use all the nice efficient implementation techniques for nominal type checking, including nominal runtime type checks, right? The implementation techniques that you have in a language like Java, without losing structural typing. Yeah, and that's all I have. Thank you very much.
Okay, thank you, Andreas. If we have any questions. And where's Ishan for the next talk? Yeah. Okay. No? Oh. Sorry. So is this being added to WebAssembly?
So this is basically the type-theoretic foundation for the GC extension, if you want.
And this is the kind of subtyping that WebAssembly has? Is this simple record subtyping? That's what you're supporting?
Yeah, record subtyping, co-contravariant function subtyping.
Okay.
What you would expect.
Yeah. Okay.
Looks like I made it look too simple.
Okay. Well, if there's no more questions, thank Andreas.